Okay, so today we're going to talk about hybridization and bonding in regards to organic chemistry. So our goals for today are determine the hybridization of atomic orbitals in a particular compound, determine which of those orbitals will participate in bond formation, and determine where a lone pair will be, which orbital a lone pair will be in if given a certain molecule. Okay, so let's review a little bit about what we know from general chemistry. So the simplest place to start is with carbon. So one of the early topics in general chemistry is electron configurations. So hopefully you remember that carbon's electron configuration is 1s2, 2s2, and 2p2. What that means is that there's 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and then we need to obey the filling rules, and we place 1 electron in each of these p orbitals. Okay, so one thing to remember is what an orbital actually is. So the working definition I'll use right now is it's an electron cloud with a given shape and an energy. Okay, so what do we really mean by that? Well, first of all, if you've seen pictures of orbitals in textbooks, in particular, we'll look at the 2s and the 2p, then you might see something like this. So remember, s orbitals are spherically symmetric, which means they just have a spherical shape, and these p orbitals are dumbbell shaped or figure 8 shaped. So that's what we mean when we say they have a shape. So s is spherical and p is dumbbell shaped. The other thing we talk about is the energies. So the energies are determined by the quantum numbers associated with the atomic orbital. So, for example, you should be familiar with an energy diagram like this. So, s orbitals are typically lower in energy than p orbitals. These guys in the middle here are what we call hybrid orbitals, and we'll talk about them in a little bit. Moreover, the principal quantum number, which appears before the designation s or p, also plays a role. So a 2s atomic orbital is going to have a lower energy than a 3s atomic orbital, and that's going to have a lower energy than a 4s atomic orbital. Okay, so one other thing we should discuss, and this might be jumping the gun because we haven't discussed hybridization, is something called p character. So p character determines how much of a orbital contribution consists of p. So an s orbital is entirely s, so no p character, and an sp is 50% s, 50% p. Similarly, sp2 is around 66% p, and sp3 is 75% p, with p being 100% p. There's certain characteristics that come along with p orbital contribution. One of those being the more p character that an orbital has, the higher energy that it has. We'll talk a little bit more about that when we discuss hybridization, which is what we're going to do next. So if you remember your general chemistry, in particular, carbon generally has a hybridization phenomenon that occurs. That is to say, this is the electron configuration we'd expect with the 2s2 and the 2p2. Then it takes these orbitals and it mixes all 4 of these together, 1 of the 2s orbitals and 3 of the p orbitals, and we get 4 sp3 orbitals. And that is what we call degenerate. So degenerate is going to be a word you hear a lot. What does degenerate mean? Well, in the context of chemistry, it means that these sp3 orbitals have the same energy. So degenerate orbitals have the same energy. Okay? So the reason why this hybridization phenomenon occurs is that typically you see carbon making 4 bonds to things, and the s orbital has a much lower energy and the p orbital has a much higher energy. Now, if carbon wants to bond 4 times the things, it gains a favorable energy if it mixes these orbitals to make something that's in between the energy of the s and in between the energy of the p. So it pretty much looks like this chart where you see the sp3 having an energy between the s and between the p. Okay, and what is some evidence that we actually see this hybridization occurring? Well, that goes into your freshman year Vsepr, or even high school. You've probably discussed Vsepr, which is called valence shell electron pair repulsion. It's another word for how do we determine the molecular geometry of molecules. So if you have a simple molecule such as CH4, what you see is a central atom, this C. You see 4 bonds, each to a hydrogen atom, and it has the shape of what we call a tetrahedron. And what that means is that the bond angle between all of these is the same, and they're equally spaced out at the corners of a tetrahedron. So why does that give us evidence that this hybridization is occurring? Well, remember, what this hybridization gives us is it takes 4 orbitals that don't have the same energy, and it gives us 4 orbitals that do have the same energy. That's what the mixing does. And if you look at each of these bonds, they're symmetric. So the bond lengths are the same, the bond angles are the same. What you're seeing is 4 degenerate bondings. So that tells us that carbon typically bonds to 4 things, and it tries to mix to lower the energies and obey this Vsepr model. Okay, so let's briefly talk about what we mean by bonding, which seems very basic, but it's deceivingly basic. So a covalent bond is the overlap between orbitals, 2 atoms, in which electron density is shared. So what you need to remember is that, again, an orbital is an electron cloud, so a probability distribution of where the electron is likely to be found, with a given shape and energy, such as 2s, 2p, in any of these directions. A bond is the overlap of 2 orbitals, and when the orbitals overlap, they share their electron cloud. So the probability density is distributed between those 2 atoms in those orbitals. And it gets more complex in regards to bond angles, bond lengths, and electronegativity, but for now let's just concentrate on the fact that a bond in general is when you have similar energy in your orbitals and good spatial overlap, and that allows them to form a bond. Okay, and with the introduction of this overlap and energy ideas, you could have in organic chemistry that you'll be doing 2 different kinds of bonds, basic bonding. One of them we call sigma bonding, which means the overlap is head-on, and we'll talk a little bit about that. And one of the bonding schemes is a pi bond, in which you get side-on overlap of orbitals. So remember, a bond consists of 2 orbitals. Orbitals have shape and energy, and the bond energy and shape depends on the overlap of the orbitals we use to create it. So when we're talking about a sigma bond, we're talking about head-on overlap of orbitals. So these are some examples of that. If you take 2 hydrogen atoms which only have s orbitals and you combine those head-on, you get an HH covalent bond, a sigma bond because of their head-on overlap. Similarly, if you have an s orbital and a p orbital and they combine head-on, and again we could say head-on means if you draw a line from this atom to this atom, the orbitals are forming along this axis. That is called the internuclear axis. If you have overlap along this axis, that will give you a sigma bond. Similarly, you could combine p orbitals head-on like this, and that gives you sigma bonds. What about pi bonds? Well, pi bonds are a different kind of overlap. It means that when the overlap happens, it happens side on. So that looks something like this. So if you take those two p orbitals and put them side to side and they come close to each other and they overlap, you get a bonding off the internuclear axis, or that plane between the two atoms. So we call that a side-on overlap, and that gets you a pi bond. Okay, so we have, again, I'm going to refresh one more time. Orbitals are probability densities of electrons. They have a shape and they have an energy. When you combine the orbitals, you could either, when you combine the orbitals in space of two different atoms and they overlap, you can get a sigma bond or pi bond, depending on how they overlap. If they overlap head-on, you get a sigma bond. If they overlap side-on, you get a pi bond. Okay. So when we're talking about a double bond, whenever you see a double bond in a molecule, that's really a sigma bond between two things and a pi bond also existing between those two atoms. So if we see ethene or something like that, you have one sigma bond between these two guys and you have a pi bond between these two guys. So a double bond is really the combination of a sigma bond and a pi bond between the same two atoms. Similarly, if we're talking about a triple bond, say in acetylene, then we have a sigma bond between two atoms, and we also have two different pi bonds between two atoms. And remember, since those pi bonds are oriented off the internuclear axis, they're going to be perpendicular to each other. So one of these pi bonds is going to be in the plane, and one of them is going to be out of the plane, and they're going to be perpendicular, or sometimes we call that orthogonal to each other. That's one of the reasons you shouldn't be able to have a quadruple bond, because it wouldn't make sense geometrically how you could even get that combination to work. Okay, so really you have a lot more possibilities when you're talking about your sigma bond as opposed to your pi bond. Your sigma bond can be formed between regular orbitals, regular atomic orbitals, so SS overlap, SP overlap, PP overlap, or any of these combinations of hybrid orbitals. Your pi bond really only comes from the overlap of p orbitals. So if you want to determine the hybridization of an atom's orbitals in a molecule, what we use is something called the steric number. So this is a formula you'll be using often. You take the atom, you look at how many lone pairs it has, and you look at how many atoms are bonded to it. If it has a steric number of 2, then it has an sp hybridization. If it has the steric number is 3, then it's sp2, and if the steric number is 4, then it's sp3. Okay. So if we understand this, we could develop a way of looking through a molecule and determining the hybridization of each one of those atoms. And that's going to look something like this. So how do you start? Well, in this course, which is Rutgers 307, we'll say that terminal atoms, and everything will make sense when we do an example. Terminal atoms don't hybridize. We won't worry about where that comes from. We'll just accept that on face value here. If the atom is terminal, it's not going to hybridize, so you're only going to have atomic orbitals. If the atom isn't terminal, it could hybridize, and you're going to get hybrid orbitals. When you're looking at an atom that you know has hybrid orbitals, you use that steric number formula to calculate if it's going to be SP, SP2, or SP3. And then you're just going to keep going and going until you've done all of the atoms in a molecule. Once you've done that, we could look at each of the sigma bonds and determine the hybrid orbitals from there. Okay. At this point, we're going to start doing some examples, because that makes everything a bit more clear. So say we are given a molecule that looks like this. Okay, so the first thing you want to do when you start to determine the hybridization is you want to simplify whatever it is that you're looking at. Say we have a molecule that looks like this. Well, the first thing that's going to trip you up is not figuring out where the extra hydrogens are, if you're unfamiliar with line wedge form, and lone pairs, because you need that to calculate your steric number. So the first thing I recommend you do is add in the lone pairs definitely, and then if you need the hydrogen bonds added in, add in those hydrogens. Okay, what do we do next? Well, if you remember back to our algorithm, we're going to look at each of the atoms and we're going to see if they're terminal or not, and that'll tell us whether or not they hybridize. Okay, so what do we mean by terminal? Well, it means that it is at the end of the molecule and it is only bonded to one other guy. So this nitrogen is only bonded to another carbon, so we're going to say this nitrogen is at the end of our molecule. What that tells us is that by our criteria, this nitrogen is going to be unhybridized. Okay, then we go along to the next atom, which is over here. Okay, this guy has 2 atoms bonded to him. So his steric number is 2, so he's going to be sp. Similarly, as we go along, over here, this atom has 1, 2, 3. Remember this hydrogen over here that you can't see because it isn't written in. It has 3 different things bonded to it, so it's sp2 hybridized. Similarly, this carbon over here has 1, 2, so it's going to be sp hybridized. This over here is going to be the same as this guy, as 1, 2, and then a third invisible hydrogen being bonded to it. And then over here, this carbon has 1, 2 bonds to it, and then 2 hydrogens that you don't see. So it's going to be, our steric number is 4, so it's going to be sp3. And then notice that this sulfur is not terminal because it has 2 different things bonded to it at least. The terminal atom is actually going to be the hydrogen, which of course isn't hybridized because it only has a 1s orbital. So the sulfur has 2 lone pairs and 2 atoms bonded to it, so it is sp3 hybridized. Okay, so one thing, there's multiple things that are notable here. So we determined the hybridization, but sometimes people want you to be even more specific. So we know that these are the hybridizations, but if you look at the periodic table, you'll notice that things are slightly different depending on where you are. So if you're in a second row, carbon is using the valence orbitals 2s and 2p. So we could call this a 2sp hybrid orbital because it's hybridizing its 2s and its 2p. In contrast, over here, you see that sulfur is in the third row, so its valence is going to be from the 3s and the 3p. So we could really call this a 3sp3 hybrid orbital because it's mixing its 3s atomic orbital and 3 of its 3p atomic orbitals. I don't think that designation is particularly useful, but someone might ask you later on to actually know that. The other thing you could do is you could find the total number of hybrid orbitals that are present here. And the way you're going to do that is you're simply going to add up the steric numbers for each of the species that we see here. So that's going to look like this. So the sp from this, the sp2 from here, the sp from here, and so on and so forth. The reason why this works, again, and I hope you're making the link between what we talked about earlier, is that you require p orbitals to be used to make your pi bond. So when you're looking at this carbon, you know it has originally 4 atomic orbitals. It has a 2s and it has 3 2p orbitals. Now 2 of those p orbitals are being used in the pi bonds here. So what does it have left? It has a 2s orbital and it has a 2p orbital. So the only things it could mix are that remaining s orbital and that remaining p orbital. And so if you mix an s and a p orbital, you need to get the same number of orbitals out that you send in, so you're going to get 2 different sp orbitals, which are going to be used in the sigma bonds to carbon. So it's saying it has 2 different sp orbitals. Over here it's saying one of your p orbitals is being used in the pi bond here, and you have 3 remaining atomic orbitals. You have an s orbital and 2 p orbitals remaining. If you're going to hybridize those, you're going to get 3 sp2 orbitals. Okay, I hope that makes sense, because that's super, super, super important. So if it doesn't make sense, rewind a few minutes and really try to convince yourself that that's what's happening here. The other thing to figure out is what's going on with this unhybridized nitrogen over here. So one of the questions you might ask is, which orbital on nitrogen contains this lone pair? Moreover, which orbital on nitrogen is going to be in this sigma bond? Well, you should remember some basic facts. You should remember that nitrogen, like carbon, is in the same row on the periodic table, and its valence means that it's going to have 2s orbital and 3 2p orbitals. Okay, but you can see that it's part of a triple bond, and a triple bond is a sigma bond and 2 pi bonds. So you know that 2 of its p orbitals are going to be used in these 2 pi bonds. So what's left? It has a 2s orbital left, and it has a 2p orbital left. So let's make light of that fact. Okay, so that means one of the remaining orbitals is going to contain the lone pair, and the other remaining orbital is going to be used in the bond. We can make 2 separate arguments here. We could say that the remaining 2p orbital that it has better spatial overlap with this sp orbital. So that's going to be used for the sigma bond, meaning the remaining 2s contains the lone pair. The other argument you can make is that the 2s atomic orbital is much lower in energy, if you remember back to this energy diagram over here. So the s is much lower in energy, and the electrons that are going to be found in the lone pair want to be as close to the nucleus as possible, because that's where they're most stable. So if they're in the 2s atomic orbital rather than the 2p, they're going to be much closer to the nucleus, and that's going to be thermodynamically favorable. So the lone pair should be located in the 2s orbital. You could use either of those 2 explanations. Okay, and lastly, if you remember back to our algorithm, we want to determine what's going on with these sigma bonds. So remember, a bond consists upon the overlap of 2 different orbitals. So if you look at the hybridization you formed for each of these, the sigma bonds should consist of the overlap of each of these hybrid atomic orbitals. So this sigma bond consists of the sp3 orbital from this carbon and the sp2 orbital from this carbon. Similarly, since this was sp3 hybridized and this was sp3 hybridized, this bond is the sigma bond is the combination of an sp3 orbital from this carbon and an sp3 orbital from this sulfur. Likewise, since we determined that the lone pair is going to be in the 2s, we know that this sigma bond located within the triple bond is going to be formed from a p orbital from nitrogen and an sp hybrid orbital from the carbon here. Okay, so I've talked enough for now, so what I am going to do is I am going to give you a practice problem. So start with this molecule, and what I want you to do is I want you to identify the hybridization of each atom that you see here. So you could ignore the hydrogens. I also want the total hybrid orbitals, and I also want the orbitals involved in each sigma bond. Okay, and I recommend right now you pause the video and work this out yourself. So one point I'll make is that organic chemistry, learning in organic chemistry is a lot like the yin-yang. So what do I mean by that? Well, you could see one part of this being the process of being correct, and one part of this being the process of being incorrect. And most people try to focus too much on being correct. They only do problems that they think they could get right, and they only want to be right, and they're afraid of being wrong. Organic chemistry isn't easy, and you're going to be incorrect many, many, many times, but that is super important to the process of learning. So you need to embrace the part of being wrong, because being wrong tells you what doesn't work, and what doesn't work is just as important as what does work. So pause the video, attempt this problem, and, well, I'll tell you how it goes, but you have to take a shot first. So okay, I'm going to assume that you attempt this problem. Let's look at how to solve it. So I recommend you take this original substrate and you pencil in the lone pairs, and if you need it, the hydrogens. So that's what it's going to look like with all that detail. I personally don't like having all the hydrogens there, so I'm going to take them off when I solve the problem. Okay, so remember, go back to that algorithm and look at each of these, determine who's terminal. So the only guy that's terminal here that's interesting is this iodine. Why is it terminal? It's only bonded to one other thing, this carbon here. The rest of the terminal atoms that are found in this molecule are all hydrogens. So that means these carbons and this oxygen are all non-terminal, so they're going to be hybridized. Okay, so calculate the steric number on each of these. This has 2 lone pairs and 2 atoms, so it has a steric number of 4. This has 2 adjacent atoms and 2 hydrogens, so it's going to be a steric number of 4. This has 2 atoms and 1 hydrogen, so it's 3. Same thing here. And this has 3 atoms bonded to it and a hydrogen, so it's going to have a steric number of 4. If you want to calculate the total hybrid orbitals, all you're going to do is add up the steric numbers, and you're going to get that. Likewise, if you wanted to look at each of the sigma bonds, you simply need to look at your hybridization and say, okay, this sigma bond here is going to be the overlap of an sp2 and an sp2. This sigma bond here is going to be the overlap of an sp3 and an sp2. In iodine, well, that's a little more difficult, but you could assume that of the orbitals that are on iodine, the p orbital has better overlap for bonding than an s orbital. So I'd say a p orbital on iodine is going to be used in the sigma bond located here. Okay, let's do one more problem, just to make sure you know what's going on. So here's your substrate, and I'll give you pause the video and attempt to figure it out. Okay, I'm going to assume that you paused and tried it yourself. So here is the substrate with the lone pairs penciled in. Similarly, we're going to go through our algorithm and say that none of these are terminal. They're going to try to trick you, and you're going to try to think that this is terminal, but remember it's not. It has hydrogens, and those hydrogens are actually going to be your terminal atoms. Okay, so this time I actually penciled in the number that should appear in front of the hybrid orbital, just in case you're ever asked for it. So remember what this number means is that you took a 2s and a 2p orbital and you mixed them. Phosphorus, if you remember, is in the third row of the periodic table, so its valence orbitals are going to be a 3s and a 3p. So when you combine to make a sp2, you're actually going to make a 3sp2. Remember, that doesn't tell you how many orbitals you're dealing with, it just tells you the mixing. So a 3s and a 3p was mixed. Coincidentally, there are going to be 3 sp2 orbitals, but don't confuse that. Okay. Similarly, if you wanted to know what's in this sigma bond, you're simply going to say it's the overlap of a 3sp2 and a 2sp. Okay. That's all for now. Make sure to master this, because you could very well see these questions on your first exam.